Okay, let's start. So today's topic is about the PFM, piezoelectric force microscopy, and the microscopy itself is relatively easy, but we will spend some time to discuss the piezo response and ferroelectric materials. So that's our main topic today, and the piezo response and the ferroelectricity is more materials related, and just in AFM theory, we will not have too much theory about that. So the topic today, I would like to spend most of the time to explain the physics first, and then it will help us to understand the AFM theory itself. So let's start with the piezo response. The piezo response. The piezo response is the piezo. This word piezo itself is from the Greek, and it just means pressure. And just in old in old Greek word, and they found this effect maybe 2,000 or 3,000 years ago, and they found a so-called piezoelectric effect. That means if we compress on the materials, they found this material itself seems charged, and we can get the potential difference on both sides. Of course, in Greek, they don't understand what's the potential, but they found this material is kind of charged, and later they found a converse effect. If we place this material inside an electric field, there will be a displacement or there will be a deformation on these materials. So we define the piezoelectric effect is we use pressure to change its charge status, and the converse piezo effect is we use a force. We use electric field to change its deformation. So we would starting some the physics first. So let's talking about the piezo effect. Piezoelectric. Yesterday we described once we have a material, if we place it in the electric field, this material will be polarized. The polarization or polarized means this material has two poles. One side is positive charge, another side is the negative charge. Then this means it has two poles. And and to describe this polarization, polarization, we would use a concept of the dipole moment. And I think most of you are familiar with this concept, dipole moment. It means we have a pole, we have a pair of two charge. And these two charges, they would not combine together due to some other effects. They just form this kind of poles. And these two poles, they have a fixed distance between the two poles. And then we call this is a dipole. And this to describe this dipole, we would use a physical value called dipole moment. I use mu to describe this dipole moment. It equals to the charge times the length between them. Since the length itself is a vector, so the dipole moment itself is vector. Okay, this is a quite simple concept. For example, you guys are familiar with the materials. For example, this molecular carbon monoxide. This is a typical dipole because the distance between the carbon and the oxygen, the length is fixed, and the carbon is charged and the oxygen is charged. So this will form a dipole moment. So we want to describe the polarizations. We just if we place a materials inside the electric field, the electric field will polarize these materials to make it as two poles. So how can we describe this polarization status? We would use physics meaning the polarization strength. Or we just simply call it polarization. We would use P, and it will be definitely a vector. And it is the sum of all dipole moments inside this material, inside this solids. And then we want to define it as a strength. So we would divide it by the volume of this whole materials. And this we can define how this materials is polarized. And of course, it will be a vector. And its its unit will be coulomb times meter. That's the unit of the dipole moment divided by meter square, meter cubic, and so it will be coulombs times meter root squares, right? That's the polarization. That's the polarization. Then next, how we describe this polarization phenomena. So in our typical understanding, this polarization is just due to an external electric field. So easily we can describe it in this way. We have the polarization. It is caused by external electric field. So to describe a materials, how it can be polarized by external materials, by external electric field. That's a way to describe the polarization of these materials. So we would use a coefficient to link each other. So this coefficient, we would call it polarization coefficient. This is used to describe how easily these materials can be polarized by external field. So usually we use alpha to describe it. Usually we would use Usually we would use alpha to describe it. Okay, that's the polarization. We have another way. We have another way to describe. We have a. Let me see if I'm using the. Oh yeah. Okay, and so when we have a materials, when we have a materials, if we apply an external electric field on it, and then this material itself will be polarized. I'm sorry, it will be this way. It will be polarized, and then itself will contribute an internal electric field. And this internal electric field is described by the P. And so inside these materials, there will be this one plus its internal electric field. So this total electric field inside these materials, we usually use another word, another physical, we call it D. And usually we would use epsilon 0 plus E times E plus P. And this way we can describe the total field, total electric field inside these materials. And this D, I think I forgot the English name. Is maybe some of you remember it. We call it electrical displacement. The Chinese will call it 电位移矢量, something like that. Okay, so finally we have the D. The D just represents all the electric effects inside these materials. So and from this we would put it in. We finally can get the D equals to the epsilon times E, and the epsilon is the so-called dielectric coefficient of this material. Okay, but the whole idea is we need to remember the concept of P. Okay, then next, this is about the polarization. We have another concept inside the piezoelectric. The piezoelectric, it means we use some force to change the polarization. But usually when we're talking about the force, we just means we want to squeeze something. We want to squeeze something. If we squeeze those things, we want to say if we can make this thing to have deformation. So usually we would have another thing, we call it deformation. This deformation is easily understand, and we use it very often even in our AFM. That's the so-called elasticity. If we have a force, our materials will have a deformation under this force. And between them, we called how these materials, we would call this materials how hard this material is. Usually, it's between them is the stiffness, right? We have the famous Hooke's law. It's the F equal for a spring, F equals to K times the elongation of the spring. That's the same thing. That's the same thing. For Hooke's law, the K we call it spring constant. But when we're talking about deformation or elasticity, we usually call K stiffness of the material, right? So, and for the deformation, we have this Hooke's law, but usually we found this Hooke's law is not intrinsic because this stiffness, for springs, we already know if this spring is longer and thinner, I'm sorry, if the spring is longer, we would know the K will be smaller. So the length is related to K, and of course, the thickness. If the thickness increase, the spring will be larger. So this stiffness or the spring constant is related to shape. But we want to describe a materials, we always want to make sure this thing is material's intrinsic properties. So we have another way to describe this deformation, or we have another way to describe the Hooke's law. Is we confine the stiffness as the intrinsic property. It's related to length. It's related to thickness. With thickness, we call it a cross-section area. And it's also related to deformation. And then we make this cross-section area goes to this side. We get the F over area equals to something times deformation divided by length. Okay, so we call this stress. We call this strain. And of course, in the material's intrinsic property, we call it modulus. Okay, so, and we write it with the stress, we usually use sigma to represent it. And the strain, we use epsilon. I'm sorry, there will be two epsilon here. So let me think. How we can, okay, I use epsilon. And I put a S below to mean it's strain, okay, to separate, to distinguish with the dielectric coefficient. And then we can write it down this, and the modulus, usually we use the E to represent it. And this, and for the electric field, I would add an arrow on it to let you know it is a vector. So this Hooke's law, we can write it down as the sigma equals to the modulus times strain. Okay, so this relationship, we describe it, the deformation. And this relationship, we describe the polarization. So then we can describe our piezoelectricity. The so-called piezoelectricity, it means we can use stress, we can use force to achieve polarization. I'm sorry. So that means the P is somehow related to sigma, or the D is somehow related to sigma. That's the piezoelectricity. And then the converse piezoelectricity, it means we can use electric field to make the material deformation. Which means the strain can be somehow changed by electric field, right? That's our way in physics. We will describe the piezoelectricity and the converse piezoelectricity. Okay, so that's the same we are going to use. Then to describe this piezoelectricity and the converse piezoelectricity, we would use thermodynamics. That's our theory beginning. So why we use thermodynamics? Because first, this materials is bulk materials. It has many atoms. It's kinds of statistics. And the second, this materials is always in a kind of a balanced or in a equilibrium. So it satisfied our thermodynamic the conditions. So the best way to describe it, we would use thermodynamics. Okay, so the process is relatively long, so I write it down in my slides, and let's go through this thermodynamic descriptions. So we're starting from the first law of the thermodynamics. The thermodynamics first law is easy, right? The energy is conserved. So the energy is conserved, so we can describe one quantity, or we can describe a function. And this function, we call it energy or internal energy. And in Chinese, we call it 内能. Okay, that's the first law. So the first law, it means if we want to change the energy of the materials, you can do two steps. You can do two types of energy exchange. The first is heat. The second is work, right? So that's the first law of the thermodynamics. The energy is conserved. You give some heat, you give some work, this energy will not gone. It will change the internal energy of our materials. So that's the first. And then the second law defines a function called the entropy. And then we get the entropy down. We use that entropy to describe the heat. And that's the second law. Okay, so the purpose here is I don't want to involve any heat here. So I gave it the entropy. So I put the entropy here. So the heat is gone. The heat is replaced by the entropy. And the last thing I would do is about the work. So I want to describe the piezoelectricity. So how many works I could do? First, I could, this is the materials. So it has a fixed shape. So I can use the force to change its deformation. And to change this deformation, it's mechanical work, right? This mechanical work is easily to calculate. It's the force times the length. So this force and the length is just the force and the deformation. So this part, the energy of this mechanical part, can be easily done. It's just the force times the length, or we write it down as the strain. That's the force. I'm sorry, stress is the force. Strain is how the deformation happens. Of course, the strain and the stress it's not related to volume. It's a single volume values. So I need 2 times the volume of these materials. So this part, I describe this mechanical work, or in the textbooks, they will call this elasticity works. You give a force, you change the deformation, the material will storage those kind of potential. So this is the mechanical works. The second works is electricity. What's the electricity done? Under the electric field, we move the charges. And we move the charges, it means we do some work inside these materials. So it will be definitely something to do with the electric field, and the charge moves. And how the charge moves is described here. We use the polarization because we move the charge distribution inside these materials. And the charge distribution, we use the polarization strength to describe it. And we consider it will also have the electric field itself. We would use the E times D, the electric displacement here. And of course, it's just a per volume value. It's a strength. So we need to times the volume here. So finally, we get this function. This du equals to TdS, and plus the electric work, and plus the mechanical work. And then we want to get rid of the volume, right? We don't want the volume here. We don't want the integral here. So get rid of the volume. So for per unit volumes, we get rid of all of the volumes. Then we get the per unit volume, the internal energy is something like this. This is easy for us. Okay, so inside my slides, I would use the blank to represent this is a vector. Okay, this is a vector. So I use the point times here. And then we finally get something we want. And what we want here is here. We want to know how the polarization or how the electric displacement is changed by sigma. Is how it's changed by the so-called stress. So we want the stress to be inside the derivative. And then if we take the second order derivatives, we can get something to do with the d over sigma. And it's the same. We want our epsilon, how the epsilon is, how the strain is affected by the electric field. So we want the electric field to be inside the derivatives. So we need to do some mathematics and to make the D is outside and the E is inside the derivatives, right? This formation and in the mathematics is, I forgot. This is this is a French name. I forgot how to pronounce this word. And in Chinese, you may remember it's热浪德. Yeah, this is a French name. So and this transformation, Legend or something. Okay, this transformation, we can play things like this. We define a new function. This new function looks like this. It has the u, it has the ts, it has the e times d, it has the sigma times the epsilon. Okay, and this new function has no physical meanings. It has no physical meanings, but it's just the way make up this kind of function. So the internal energy U has the physical meaning. It is the energy inside the materials. But this new function has no meanings, but it's famous. That's the Gibbs free energy. And then for this new values, we take the full derivative. And for the full derivative, we just do the derivative on every term. Okay, on every term, we can expand. We can get this, right? And then we already know the du equals to this one. So the du minus those things, the final thing we get is this. So finally, the electric field is under the derivative and the stress is under the derivative. Okay, so, and then we can change the electric displacement to polarization. And finally, we get this term. Okay, when we get this term, the second step we will going to do is to take the second order derivative of Gibbs energy. Okay, so and that's the basic relationships of the second order derivatives. Since G is a function of electric field and the stress, so if we take the second order derivatives, we can do electric field first, or we can do the sigma first. And we change the sequence, we does not change the value, so it should equals to each other. Okay. So the G over E, that's the polarization field. So I'm sorry, polarization strength. So the polarization strength over sigma, what's this one? That's the piezoelectricity. And the G over sigma, that's the epsilon, that's the strain. What's the strain over electric field? That's the converse piezoelectricity. So this equation just told us the piezoelectricity and the converse, I'm sorry, it should be converse piezoelectricity, they fully equal each other. So it's the same thing, just a different way to watch it. Okay, that's our thermodynamic description told us. So we can just use one term to describe this thing. And this term, we call it piezoelectric coefficient D. Okay, so that's our that's the whole description here. And then in the future works, you may say different you may say different description of this piezoelectricity. When we're talking about piezoelectric effect, we mean how the stress change the polarization. And the polarization, the unit of polarization is Coulomb per meter square. And the stress is Newton per meter square. So the polarization, its unit, okay? Sorry, I don't have my, oh, it's here. So the unit here will be Coulomb per Newton. And for this for the converse piezoelectric effect, it will be strain over electric field. The unit of strain is 1, right? It has no unit because it's meter over meter is 1. And the electric field is voltage per meter. So the units of the converse piezoelectricity, it will be meter per volts. So this unit stuff, it's almost the same. The old Greek guys, they described, you apply a force, you change the charge distribution. So it's the Newton, how it changed the Coulomb. And for the converse electricity, you apply a voltage, you change the displacement. So it should be meter over volts. Okay, that's how the Greek guys, they understand this two concept. But for us, we need to know we are doing strain stress, we are doing the polarization and the electric field. So not just those the volts, the Newton stuff. Okay, that's our first topic here. So how we understand the piezoelectricity and the converse piezoelectricity. Okay, it's clear, right? It's kind of long, but yeah, it's thermodynamics. So it's for equations. We follow the equation, we can get the results we want. Okay, so in physics, we understand how this piezoelectric and the converse piezoelectricity works. Is okay. And the second we need to do is how we describe it in mathematics. Okay. So let's go back to here. Let's go back to the to here. Let's go back to the stress and the strain. So the stress and the strain. So we define the stress as a force over area. So the force, in our understanding, the force should be a vector. And what about an area? Area itself also has a direction, right? We we describe this area, we would define how its direction is defined. It's defined by our hands and follow the boundary of the area. We will have the direction of this area. So the area itself will definitely be a vector. What about the deformation? Our material can deform, follow a certain deformation, so it should be vector. And the same as length, it will also be a vector. So a vector divided by a vector, what's this to? Per my understanding, it should not be one number, or it should not be a simple vector, right? It should be some complex physical values. So how we describe this thing? So we do a brief introduction. Is this kind of materials in physics is the tensor. So the tensor is just we have know the name tensor several times. It just means a value, and the formation of this value does not change as our coordination. So we use the vector as a beginning. So these vectors, this vector, we call this red arrow. This red arrow is absolutely a vector. So this vector, to describe this vector, I have a certain way. I can put this vector inside I defined coordination. And inside this coordination, I can use two numbers to describe this vector. It's 0, 5. And then I change my coordination and to this new one. And then inside this new coordination, to describe this red arrow, I should also use two numbers. But the value of the number has changed to some other things, 3, 4. So this vector, to describe this vector, I should use this formation. This formation means I need two numbers to describe this thing. The value of these numbers can change, but it has to be a pair of numbers. It has to be two numbers. This kind of formation is used to describe the vector, not the number 5. So for this kind of thing, this formation will not change if we change the coordination. So we call this thing a vector, or we can say this is a two-dimensional vector. Oh, I'm sorry, two-dimensional tensor. Okay, second thing is the Einstein story when they are studying the theory of relativity. So it's a famous one. So inside a train, and the train is moved, and the train is moved at a constant speed v. And then on top of this train, there is a charge, and the quantity of this charge is q. And then inside this, there is one guy, and he is inside this train. Because he is inside this train, so he is moving the same speed as this q, so they are relatively static, and they would only say this q will generate an electric field, right, inside the train. But if we have a medium, if we have someone outside this train, he is static, okay, and so he would say this charge is moving at speed v, and for a charge moving at speed a, he sorts a magnetic field, right? Because the Lorentz force or the current will generate so-called the magnetic field, right? The directions, something like this. Okay, so he would say, there is a charge, so this charge will generate electric field, but this charge is moving, so there should be a magnetic field. right? Then the Einsteins or those, I forgot the name, is Lorentz or some guys. So they would say that's the same phenomenon, right? That's the same phenomenon in our world. This thing should not change how we say this word, how we describe this thing. Inside, we only say electric field. Outside, we say both electric and magnetic. So the electric and the magnetic itself, they are not a good way to describe this thing. Just like this one. The 0 and 5, they are not good enough to describe this vector. They combine this pairs describe this vector. So the electric field and the magnetic field, they are not good enough to describe the electricity. So we need to make them together, right? So that's the famous electric and magnetic tensor, right? I forgot how to describe it. It's something like this. So it's E X E Y E Z, and that's the B. I'm sorry, maybe BX BY BZ, and that's the BX BY BZ, something like that, right? That's the electric magnetic tensor. Okay, so we want to say here is the tensor is just a complex the factor. It's used to describe the physical properties, and these physical properties, its formation should not change against the coordination, right? It's the same property. It should not change how we say it, right? We can say it in this coordinate, we can say it in this coordinate, but it's the same thing. We can say it inside the train, we can say it outside the train. It should be the same thing. So if we only say electric field, we only say these three terms. If we are outside the train, we say both of them. So we'd better to describe in this way. So that's the property of the tensor. Okay, so the tensor means its formation does not change as the coordinate changes, right? So with this, we would know how we can describe the stress and the strain and our piezo electricity coefficient. Okay, so the first tensor we will just go through it briefly is the stress and the strain tensor. So I remove this one. So name call it deformation. So we go from the sigma first. So the sigma is the F over A. So the easiest way to describe it. So the F, so we can say the F is sigma times A. So the F, it should have three components. Fx, Fy, Fz. And then our area, it should also have three components. Ax, Ay, Az. It just means the force does not need to be perpendicular to our area. They can They can be at any directions, just like this one, right? It can have any directions. So our sigma itself. So to describe the relationship between three components and the three components, the easiest way is we use a matrix to describe it, right? So this matrix, it has three components. It has three components. What about this one? It should have 9 components, right? This 9 components, I have write it down as this one. And in the symmetry, these components should be, this matrix should be components. And so our physics is just write down in this one. Since it's symmetric, this one equals to each other, this one equals to each other, this one equals to each other. So we only need 6 terms to describe it. And one Russian guy gave these numbers, 1, 2, 3, 4, 5, 6. So that's the stress. And the same thing as the strain. And so we have the stress, we have the strain, and then let's go to the piezoelectricity. So the piezoelectricity, we write down in this way. The piezoelectricity is P equals to something of the sigma. Since the sigma has 6 components, our polarization is a vector. So we define that in this way. And then the converse piezoelectricity is the same thing. So we can write it down in this formation. So that's once maybe you have done something with the piezoelectricities, the famous components is the D33 or D33. And this D33, we can tell easily from this tensor description. That means it's the force, the number 3 force. And this number 3 force is this Z component. So it's the force perpendicular to our area at Z. So that's this 3 means. So that's the stress at the Z direction cause the polarization at Z directions. So that's my D33 means. Or we can understand here. The electric field at the Z directions cause the deformations on Z directions follow the Z axis. So that's our definition of our D33. Of course, we have the D34 and the D35. That's another famous components we will use in our later PFMs. Okay, so this is about the tensor way to describe the piezo coefficients. Okay, so we just do a brief summary because I'm sorry, it's just in this page. It's kind of complex, and so we just want to get the concept that the so-called piezoelectric is just to polarization by the force or the deformation by the electric field, and they are the same phenomenon. They can be described using the same coefficient, and this piezo coefficient should be not a single value. It should have many parameters. It should have many components, and for this kind of coefficient, we use the model tensor to describe it. Okay, and we need to know how this thing is notationed. They use this kind of fashion to rotate it. Okay, and get familiar with the famous D33. Okay, then let's go to next. this thing we will jump. We just we don't want to spend time to hear. But the theory we need the results we need to be familiar with is how we can I'm sorry. Since we have the 18 components for a piezoelectricity coefficient tensor, it will make us very difficult to fully understand this thing. So a way to help us to reduce our calculations, we use symmetry. And the results is that if a material, it has a inversion center, then it cannot be piezoelectrics. I make a brief example to let us understand this symmetrics, the case. So we use carbon dioxide as the example. A carbon dioxide itself is, of course, it has an inversion center inside here. And so this one is it has an inversion center. And since it's nonpolar, right? This molecule is fully symmetric, it's nonpolar. So the P of this carbon dioxide is absolutely zero. And then we stretch the materials using some stress. And I just stress these molecules in this way. And then I stress the materials. And again, this material, this molecule is still nonpolar because it has an inversion center. I stretch this one, and this one will go to the same directions. So this one, the P is still zero. So I gave it some force, but the polarization does not change. So the piezoelectricity is inactive for this one. Okay. So let's take a look at another example. This one is a famous unit, which is the radium nitride 氮化镓, right? Or boron nitride 氮化硼. It's the same thing, right? So for this kind of molecules or for this kind of crystal, if we stretch it under some under stress. Of course, this one at the beginning, the polarization is zero, right? The center of all the positive charges here, the center for all the negative charges are here. So this one is non-polar, but itself has no inversion center, right? This one is not inversion center. It's this way. So it has no inversion center. And then I stretch it. I stretch this one under these directions. So in this way, we can say the left side, it has two negative charges, and the right side has two positive charges. So there will be a P, there will be a dipole moment here. So this one is, the P is not zero. So I apply a force. I change the polarization stress from zero to non-zero. So this one is piezoelectric, right? So the idea here is the piezoelectric depends on the symmetry of our materials, either molecules or crystals. If our crystals were molecules, it has the inversion center. It is piezoelectric inactivity. If not, it is activity. Okay, so if we get that, we can make we can make it very easy to study the piezoelectricities. So once you want to know your materials is piezoelectricity or not, the first thing we will do is not to test the piezoelectricity directly. We do not squeeze it to see if the polarization changes. No, we will just do the structure study first. So if it's moleculars, you can just do the X. You can do X-ray. You can do the infrared. Do many things to get the structure first. If it's crystal, again, you do TEM. You do the XRD first to get its structure. From the symmetry of its structure, you can know if it's piezoelectric or not. Okay? So that's the first thing about our piezoelectricity. Okay? Any questions? Not easy, not that easy, but it's just a way to describe it. Okay? So we can go through. You can go through that in after this class, but the key point we would like to is just summarized in this slides. They are the same, and the way to describe use thermodynamics, and we use the tensor to describe its components, and the significant components is the D33. Okay? Then let's go next. Next, we want to study the so-called ferroelectricities. But before ferroelectricities, we would starting with the so-called the pyroelectricity, because with this the so-called the pyroelectricities, we it's also described. It's also discovered by the Greek guys. They just found if I increased the temperature, I found the polarization can be changed, and this kind of phenomena they just call it pyroelectricity. It means I can use temperature to change the polarization. So this relationship can be easily write down as the polarization equals to P times change of temperature. And then, of course, the temperature is a scalar, and the polarization strength is a vector. So this is very easy. So our pyroelectric coefficient is just a vector. It's a first rank tensor. And then we can grab the, I'm sorry. I erased the equation there, but we can write it down. The Gibbs energy is the negative entropy times temperature, and it should be minus minus, there should be, okay, polarization times the electric field, and there should be a strain times stress, something like that. And we can do the dg over dt, and then do dE. It should equals to dg over dE times dt. Okay, so this right term should be G over E. That's the polarization field. Polarization strength can be changed by temperature, equals to the entropy can be changed by electric field. Okay, so this one is our pyroelectricity. So that means the temperature can change the polarization, and this one, we call it electrocaloric, and we can use electric field to change the entropy, and in Chinese we call it 电卡. Okay, just something more about the physics here, but Yeah, we just care about our pyroelectricity. Okay, the pyroelectricity means we change temperature, we change the polarization, but the temperature itself is a scalar. If you change temperature, every direction should change. So if we want our polarization to be changed by a scalar, it means the polarization itself cannot be zero. So if our crystal or our molecule itself is polar, it will absolutely has the pyroelectricity. So it means, huh? Oh yeah, it's here. That's we jumped one slide about the Newman's principles. I write it down in my textbooks, but we can give a brief introduction here. The polarization is changed. The polarization strength is changed due to the pyroelectricity times temperature. The temperature is scalar. Inside this volume, if you change the temperature, everywhere the temperature should change. Right? That's the point of the scalar. It has nothing to do with volume. It has not, I'm sorry, it has nothing to do with the direction. So this one has nothing to do with the direction, but the pyroelectricity or the polarization is related to the temperature. So it means if this thing is non-zero, it only means this molecule or this material itself is non-polar. Because temperature, it has nothing to do with the direction. You want this to be non-zero. Your material itself has to be non-polar. If the material is non-polar, it means your material, your crystal or your molecule itself, it has a polarization, right? So that's the principles behind this rule. That's the so-called Newman's principle. Okay, so then we can easily to define the pyroelectricity vector. This one should be follow the axis of our molecules. For example, the water. Water is polarized, right? So it has a dipole moment in this direction. So so if we want to describe the pyroelectricity's directions, it should be follow the same direction. Okay. So finally, we can go to our ferroelectricity. So the ferroelectricity is based on the pyroelectricity. And if a thing is pyroelectricity, means it's non-polar. If it's non-polar, it means these materials should be polarized. If it's polarized, let's define it as this direction. Okay? And a ferroelectricity means if we apply a electric field, we can change the polarization of these materials to another direction. So that's the meaning of the ferroelectricities. Okay, so let's take maybe 10 minutes break, and then we can describe more about the ferroelectricities. That's the key point today. Okay, so sorry, it's many physics this morning, but yeah, that's the thing. And after that is the PFM is relatively easy. Let's go to our main topic today. That's the ferroelectricities, and we will spend some time here to describe this phenomena. So again, it's about the ferro. So this ferro in Chinese word we all know is just 铁, right? This ferro just means a metal. It's in all the Chinese word. We found this phenomenon. This phenomenon we call it ferromagnetic. This ferromagnetic just discovered on 3 kinds of famous metals. This 铁, 钴, 镍, ferrous, cobalt, and nickel. Okay, on these 3 materials, on these 3 metals, we found this thing has a magnetic. It means it has 2 poles, the north pole and the south poles. And we found without external magnetization, it has 3 poles. It has 2 poles. And these 2 poles can be changed by external magnetic field. So Chinese guys just found, okay, this one is so special, and they call this metal 铁. But in old Greek word, in old Greece, they also find this ferric, cobalt, and nickel. They also find this ferromagnetic the materials. And in their word, they call this metal ferro. It means this materials has magnetic property intrinsically. And that's this intrinsically, or in Chinese we call it 本来就有的, 固有的, means ferro. So they want to say the ferro, this metal, it has magnetic property. It has 2 poles, it has north poles, it has south poles. I don't lead to magnetics on it. It has 2 poles. So it intrinsically has 2 poles. So they call this ferrous, means intrinsically. So that's the word ferro means in this case. And so the Western science, they did this science research, and they can understand this word. Ferromagnetic means this materials is intrinsically magnetic, but once it's translated to Chinese word 铁磁效应, nobody understands what's the 铁磁效应, but for English they understand. Okay, it means it's intrinsically magnetic. Okay, and then in 19th century, finally, there are some researchers, and they are study the crystals, and they dig in the whole world. They finally find a salt. I forgot the salt. The name of the salt is quite long. It's Latin name. They find a certain salt, and they found this salt similar as ferro. That this salt intrinsically has 2 poles. One pole is positive charged, another pole is negative charges. So they think This thing is the similar as the ferrous, cobalt, and the nickel, that which is intrinsically magnetic. They found that this kind of salt is intrinsically electric pole, right? It has positive charge and negative charge. So they call this kind of materials, also they call this crystals ferroelectricity or ferroelectric. That's those word. That's this why this word is ferro, because they know the ferro is intrinsic, and then it translated into Chinese word 铁电效应. Nobody understands that. Okay, so that's just the way different to describe it, but yeah. So and then we understand the ferroelectricity, what it means, and then from this meaning we can know it wants to describe this property. This material, this crystal, is polarized. It has two poles, positive and negative. It's intrinsically, I don't need to use electric field to polarize it. It's intrinsically polarized. Okay? Since it's intrinsically polarized, it's absolutely ferroelectricity. Since it's ferroelectricity, it does not have inversion center. So it's absolutely piezoelectricity. So our topic today is we want to study ferroelectricities. We want to study those materials are ferroelectric active, such as, say, this PZT, such as some famous 2D dimensional, two-dimensional materials. That's the hot spot today. We want to study the materials, the ferroelectricity materials of these materials at nanometer scale. Since this material is piezoelectricities, so we will use AFM to study piezoelectricity of these ferroelectric materials. Okay, that's our logic today. That's the purpose of the PFM ideas. Okay, it studied the piezoelectricities. It's based on piezo effect, but our purpose is to study ferroelectricity material. Okay, so let's spend the time to know more about the ferroelectricity materials. So we will use the famous ferroelectricity materials. PZT. The PZT, the full name of the PZT should be lead, and it has the titanium 1 - X and O3. Its crystal structure is the same as the famous perovskite. It has the same crystal structure of this process, perovskite, right? That's the name. In Chinese, we call it 钙钛矿, right? So the crystal structure of this one, the famous one is a cube. Okay. On the corner of the cubes, we have the, I use the green. We have the calcium. Okay, and on every face of these materials, on every face of this cube, we have oxygen. And if we take out the oxygen, we will find that the oxygen forms a octatron. Right? 八面体. And then in the center of this cube, there will be a titanium. And so we can say this titanium is surrounded by 6 oxygens. And since this is completely symmetric, so this one is non-polar. Right? This one is non-polar. Okay? Where's my erase? Where's my erase? I hate the materials to high temperature. And then I reduce the temperature quite quickly. I'm sorry. I reduced the temperature quite quickly. And then I found I can get an elongated crystal structure like this. I get an elongated cube. So it's the same. The calcium, I don't draw. Calcium is in the corner. And the oxygen is on the face. And the titanium is in the center. Again, this one is still symmetric. Okay? If I somehow made some changes, I don't use the calcium. I change it with the lead. And I dope some titaniums with this atom. And then I change the shade, I change the radius of the center atoms. Some of the atoms is so large, it cannot be surrounded by these 4 oxygens. So it's squeezed up or down. So I finally form this kind of structure. So the center atoms is not in the center. It's either up or down. So you can tell this crystal is no longer non-polarized. It's polarized, right? Because the titanium is positive 4 charge, and the oxygen is negative 2 charges. The 3 of them will be negative 6, right? So then this kind of structure is no longer polarized. I'm sorry, it's polarized. Okay, it's polarized. So it will have a dipole moment, or it has a polarization, and the polarization is non-zero. So this kind of structure, we would say it's absolutely paraelectric. Okay, and if this structure, we have the titanium on top, so in principle, we can have the titanium on bottom. Okay, that means if a material is pyroelectric, or if a material is polarized, in principle, it should have 2 status. The one is titanium on top. The another one is titanium on bottom. It means it should have 2 polarization. One is facing up, one is facing down. Okay, that's the basic idea we describe from the crystal. Okay, just based on the structure of the perovskite. okay? But we should have some theory to describe or have some theory to prove this phenomenon. If we have polarization, we should have two status. These two status, the polarization strength is the same, but the direction is different. Okay, that's the theory to describe the ferroelectricities. And my slides next is a way to prove this phenomenon. Okay, and this theory is come up by Landau. It's the Chinese name is Landau, and it's very long, so we don't do it quite slowly, step by step. But I can just go through it with you quite quickly. So we're also starting from the internal energy, and we do the transformation to get the Gibbs energy. And then at this time, we only need to study the ferroelectricity. So it's the electric field to change the polarization. So I don't need the mechanical work here. So I only have the electric works. So I get this deformation, something like this. Okay, and then for this one is derivative, so I will do integral. I will get the Gibbs energy, something like this. Okay, and then for the Gibbs energy, as I said, this thing is transformed from this nonpolar phase, nonpolar status to polar status by change the temperature. And this temperature is quite famous. You all know is the Curie temperature, right? This Curie temperature is not Madame Curie, it's Sir Curie, okay? It's his husband, it's her husband, okay? When we reduce the temperature over beneath the Curie temperature, we should transfer from this nonpolar to polar. So we consider if we are above the Curie temperature, we should be nonpolar. And then once we reduce it beneath the Curie temperature, we consider more. So we again doing the Taylor expansion, and our Gibbs energy or our electric displacement should be related to the Curie temperature. So we involve temperature here. And then we finally get this result. So this one, we want to say that E will change the D. So we finally get this one. Okay, so the D or the polarization can have two solutions. One is positive, one is negative. That's the one we want to prove here. If this materials is polarized, it should have two status. Okay, that's the theory we want to prove. It's just if we understand from the crystal structures, it's relatively easy. But if you need a thermodynamic proof or a thermodynamic description, we use this Landau theory. Okay, this is relatively long, so I leave it inside this textbooks if you want to use that as a reference. Okay. So finally, I just want to prove here, if it's polarized, it should be two status, and this two status is coexistence. Okay, that's the idea we want to prove here. Okay, so the next thing is if we have two status, one is facing up, one is facing down. If an electric field can change the status from this one to this one, then we call this material ferroelectric. If not, it's just a paraelectric. Okay, so in theory, we actually cannot distinguish the ferroelectric and the paraelectric. The theory only prove that if it's polarized, it should have two status. But if this two status can be changed by electric field, it has to be done or it has to be proved by experiments. Okay, and of course, if you are familiar with some structures, you can understand why this will be happen. For example, if we have this structure, we have a titanium on top. And if we change this titanium to another materials, to another ions, say, what's the atoms beneath? I forgot. I just randomly pick one. Say this one. And we know the size of this one is larger than this one. So I want to use the electric field. I'm sorry. I want to use electric field to transfer these atoms from top to below. I would guess, or I would imagine the electric field, I'm sorry, should be this one, I'm sorry. I would imagine this electric field will drag the titanium's atoms to go through this holes formed by oxygen. If this atom is too large, it cannot squeeze in, right? So our theory can only tell us it can on top, it can on beneath, but it cannot tell us if this if this electric field is strong enough to drag it down. So that's the experiment needs to tell us. So so we do it again here. The theory can tell us it has two status, and we need the experiments to tell us if this two status can be changed by the electric field. If yes, it is ferroelectric active. If no, it's non-ferroelectric active, but it is still ferroelectric. Okay, so we have many material science here. So they are the master of structures. They just play around with these atoms. Okay, they change the structures. They dope the crystals with several other atoms so that it can conquer this dynamic issue. Okay, so that's the theory here. So let's go to the next topic. For the ferromagnetic, it has the famous hysteresis loops. How about the ferroelectricities? So let's just imagine. So let's just imagine why this ferroelectricity is discovered in 19th century, but the ferromagnetic is just in Greece. Today we would know the electricity is always stronger than the magnetics. And in the magnetics, we can imagine for those old peoples, how they can find these things. They can just find some metals and they found, oh, these metals can be sucked on this ferro. They say, wow, this one is ferromagnetic. And here, we would imagine we have some sweaters, we have some things, which one is already charged. And then these charged materials can be sucked or repulsed by these crystals. We would say, okay, this one is intrinsically charged or intrinsically polarized. But if you have this kind of crystals, and you expose these crystals inside the atmospheres, can it exist stably? No, because it has so strong energy. It has a strong electric field. It will suck everything in the atmospheres to cover its surface. And it will make us very hard to find this kind of structures. That's why we discussed it so late. And we can consider if we have these things, it will generate an electric field, right? It will generate an electric field. If in the world it has another crystal next to him, how these two crystals will stay close? It will not this way, right? It will not to get close in this way, in this fashion. They will change directions, right? If we have two structures, they stay together, they will be something like this. And then you will find the electric field is from here to here. So the electric field is less exposed. Next, I have another two. This another two, how these two get close with this two? They will not form in the same direction, right? They will just form this direction. So this electric field will just in between, right? In between. So if you consider you have many this kind of crystals, they will do this kind of connection. And as a result, no electric field is exposed internally. Since there's no electric field exposed internally, we cannot discover, right? That's why the ferroelectricity is only discussed. It's only discovered in 19th century because it's so strong. But the magnetic is weak. Since it's weak, it can stay in the atmospheres. And then we can discover it in the old China or in the old Greece. Okay, that's why. Okay, and then in this kind of fashion, we would find in a certain area, it will form a kind of same directions. And in the same, the crystals, they form in the same directions. We call this one a domain. They will form many domains inside the crystals, something like this, okay? So we get the concept of the domains we can imagine. So this one, the total crystal together, it forms many domains. And as a result, the total polarization finally equals to 0. Inside each domain, it has different polarizations. And so the total polarization is 0. So I can write down in this way. It's just a sum of small domains together, right? And since the total is 0, and I imagine my structure has only up and down, so I can imagine it in this way. So I have the 50% is facing up, and the 50% is facing down. So the total polarization is 0. And then if I apply an electric field on it, how would it change the polarization? So that's our idea of the so-called hysteresis loops. So let's try to draw it. So we will have this kind of thing. So we want to check the polarization change against external electric field. So at the beginning, at the time equals to 0, it's this status. It's non-polarized totally. So the P equals to 0 equals to half facing up, half facing down. Okay, so the beginning point is here. I will increase the electric field first. So I use the blue to means I increase the electric field, and the red means reduce the electric field. Okay, so when I increase the electric field from here, so I would imagine those facing down polarization domains, if I apply a facing up electric field, I will change those facing down to facing up. So once I increase the electric field, the numbers of facing down polarization should reduce, and the facing up should increase. So the total polarization should be increased, right? So I continuously increase until at this point, the whole facing up, facing down polarization has changed to facing up. So at this point, I would guess the polarization equals to 1 times facing up. Okay, so that's this point. And on this point, what will happen? We have the basic idea that polarization equals to the polarization coefficients times E. This alpha in Chinese we call it 极化率. So we increase the E, the P will slightly increase. I slightly stretch the crystal. So the polarization will still increase against the E, but quite slow. Okay, so I increase the E at this certain points. Okay, then I decide to reduce my external the external electric field. So I reduce my polarization. I reduce the electric field. Once I reduce the electric field, in this quadrant, we still need to follow this directions. We still need to follow these relationships. So I reduce the field. I should follow the same curves, goes to these points. On these points, the polarization is 100% facing up. With a positive electric field, I cannot change the polarization from facing up to facing down. So I still have to follow this line until I get these points. At these points, the P is still 100% facing up. At this point, the external electric field is 0. So this one is non-doubt series results. This one. That's the series tells us. So, and at this point, we call this polarization the intrinsic polarization, or we can call it remnant polarization. Okay, so keep going. We will reduce the electric field continuously, but after this point, we change the electric field to this way. So we will apply elective directions electric field. We will change this facing up to facing down. So at this point, from this point, the polarization of facing up goes to the facing down. So the total polarization will reduce significantly until to this point. At this point, the total polarization is half facing down plus half facing up. So the total polarization will be 0. And then this point, we finally changed the polarization up to down, half of them. So this electric field, we gave it a name. I'm sorry. Okay, I used the green pen. Okay, we gave it a name, coercivity, 绞完场. Okay, keep going. And after this points, we keep going. We keep reduce the electric field. So we will change all the left facing down to, facing up to facing down. Until at this point, the polarization equals to 100% facing down. Okay, and after this point, we cannot change the direction. We have to go back to this one. So the slope will get slowly. And then we get it back. We increase the electric field. I use the blue pen again. I increase the electric field. So I will follow the same rule again to change the polarization. Okay, at this point, it's still 100%. Then I keep increase the electric field, but the direction of my electric field is still facing down, it's still negative. So I cannot change the direction of the facing down to facing up. So I can only reduce the polarization following this equation until I reach these points. At these points, the polarization is totally facing down, 1 times facing down. Okay, so this point is another solution of Landau theory. So that's why this theory gives a positive and negative here, because these two polarization should be that different in direction but same in value, which is the crystal structure shows here. The titanium is up or titanium is below. Okay, so this one we also call it intrinsic polarization, or we also call it remnant polarization. In Chinese, it's 固有极化强度或者饱和极化强度。Okay, and then we continuously increase the electric field. So finally, the electric field goes back to this direction. So we can change the facing down to facing up. So our polarization will increase dramatically until this point. I'm sorry. At this point, the polarization goes back to half facing up, half facing down. So this is another coercivity, right? And the total polarization will be 0. So, and then we continuously go to this point. Sorry, it's so ugly. I make it beautiful. Okay, then we finally get this loop. And then this loop, we call it hysteresis loop. We call it hysteresis loop. And some textbooks will call it ferroelectric hysteresis to distinguish with the ferromagnetic hysteresis. For the ferromagnetic, it has totally the same, but we don't use the P here. We use B here, right? We will use B for ferromagnetic to represent its magnetization. Okay, so that's our K idea. K idea today is the hysteresis loops, and from here we have 4 important points. Oh, is the time? We have the 4 famous points here. This 2 is the intrinsic polarization. It can be calculated using non-dot theory. And this 2 is coercivity electric field strength. And this coercivity, this coercivity, it has the units of the volts per meter because it's the electric field, because it's the electric field. And when we do experiments, we will not apply electric field directly. We usually to apply a voltage. So once we apply voltage to achieve this, we will call this coercivity as the switching voltage or switching bias. Okay, so no matter how, so these 2 points, coercivity, and these 2 points, intrinsic polarization, defines this final hysteresis structures. If the coercivity is small, it means this structure is easily to be switched by the external field. If this coercivity is large, means this crystal structures is very hard to change its direction. Okay, so the number of the coercivity is hard to calculate using theory because as we said, this coercivity is related to dynamics. If the atom is large, it's hard to squeeze it's hard to squeeze this oxygen windows. Okay, if we are talking about the perovskite structures. Okay, so this coercivity usually is decided by experiments, and the intrinsic polarization, yes, we can calculate it using non-Gauss theory, but usually it's also discovered using the experiments. Okay, and that's one point. We have very important 4 numbers, but actually these two equals to each other. It has just a lective, and these two equals to each other. Okay, so this whole hysteresis loops, they are symmetric. They are symmetric. Okay, that's important. Second, in the textbooks, they will call this hysteresis loops. It is anti-clockwise. This properties means if we want to switch the direction of the polarization, we have, for example, if we want to switch from facing up to facing down, we have to use lective electric field. So the coercivity on red lines, they are in the lective. If we want to switch in facing down to facing up, we have to apply positive electric field. So the coercivity on the blue curves, they are positive. Okay, so this kind of direction is quite important. If your experiment results is something like this, it's almost the same, but this one is not correct. This one is the correct direction. Okay, so it's just a quite simple the physics. You cannot let it facing down with a positive field. You cannot let it facing up using a negative field. So it has to be counterclockwise. Okay, so that's the thing about our hysteresis loops. So the most important structure, the most important thing is the hysteresis loops, and it will form those domains. Okay, so the ideas in the 21st century, I remember the piezo response is the PFM is invented in later in late 90s I think it's around 2000 years, and in that years they want to study the domains at nanometer scales of our crystals. So they invented a microscope to study that. And if we can get the hysteresis loops also at nanometer scales, that will be great. So we invented the PFM to do that. Okay, so let me check the time. Okay, still have half an hour. So that's about the crystal structures. So based on the group series, we have 32 crystal groups, and we have the piezoelectrics demands our crystals should have no inversion centers. So only 20 of them is piezoelectrics, and then 10 of them is pyroelectrics, means this structure is polarized. So only 10 of them is pyroelectric. And then pyroelectricity is this can be described using non-dot theory. And if it's ferroelectric or not, it means if we can find the coercivity, if we can find, it's ferroelectric. If not, it's non-ferroelectric. Okay, that's the pyroelectric. So from this, we can tell if we want to study the ferroelectricities, we can just use piezoelectric to do it. Okay, that's the idea of the PFM. Then the next, okay, I think I missed one slide here. So let's go through that. So this is okay, right? This is no problem, right? That's the most important part. Okay, so once we know the idea here, we need to find a machine to study the ferroelectricity. And this machine, and it's, I forgot the name, it's the English name is ferroelectrical analysis. And in Chinese, we just call it 铁电分析仪. It's a macro scales structures. And the principle here is we just want to, the idea of the ferroelectric is we want to get the hysteresis loops. So we just build we just build a chamber. And inside the chamber, we put our crystal or we put our materials in. And then we describe, and then we invent loops. And this loops is like a capacitor. And we can adjust the voltage here. We can adjust the voltage here. And then once you adjust the voltage, you just change the polarization here. And you change the polarization here, it means we can use another capacitor to study the charge distribution on these crystals. So the capacitor on another directions is used to study the polarizations. And then we use this kind of loops. We can get the P over E structures. We can get the P over E loops. That's the ferroelectric analysis they are doing. So if you say this kind of this machines, it has just large chambers, and then you have a controller to control the voltage, and you have a controller to rate the capacitance, something like that. It's relatively easy. It's straightforward machines, and that's one way to study the ferroelectricities. And with that, you can directly get the hysteresis loops. But as we said, we can do structural study. If you want to know if this materials is ferroelectric or not, you can do it from the structure study. If you have TEM, high resolution TEM, if you have the X-ray, you can study its crystal structures. If you found that this crystal structure is polarized, it's definitely pyroelectric. And it's pyroelectric, then you at least you have the serial guarantee this one could be ferroelectric. If you find the crystal structure is non-polarized, then we can continue our material study, right? To change atoms to make it back to be polarized. Okay, so that's one thing about the crystals, about the structure study. Okay, so in your future, you may want to invent, you may want to discover new materials, and you want to test if this creates your structures, your materials. For example, you find some new two-dimensional materials, quite new structures, quite good properties. If you want to know if it is the ferroelectrics, don't directly go to the SAIN or PFM. We do structure study first. You either do TM, do X, maybe 2D materials is hard to add to XRD, but do TM is easy. And the TM, you can see the crystal structures, and you can tell if it's polarized or not. I remember there is another machine, I forgot the name, but it is used, you know the light is polarized, the light 偏振, and if we use the polarized light, I will find the name of the machine and let you know in the afternoon. If we use a polarized light to shine on your materials, if the materials itself has the polarization, it will be interaction with the polarized light. And then its absorption will tell you this material is polarized or not. If it is polarized, you can go ahead to do the hysteresis or the PFM. This thing is more like optical instruments, and it's easily to be done on the 2D materials. And if you hard to do TM or do X-ray, you can do this study first. Pardon? No, it's not CD, because CD is the it's not decrometer. Pardon? Yes, SHG, yes. Second harmonic G represents what? Yes, that's the name. That's the name. SHG. We use the polarized the second harmonic terms to study the polarization. Yes, we can do that. We can do that to tell us if it's polarized or not. The CD cannot do it. CD is still it eclipse the lights. It can just turn the polarizations, but it cannot tell us the material is polarized or not. Yes, SHG. Yeah, that's the name. That's the name. That's the name. Yes. So we have new materials. We either do crystal structures or we do SHG to tell the materials is polarized or not. Okay, so that's the thing. And then finally, we can go to PFM. So the piezo effect, the ferroelectricity, it has the hysteresis loops. Okay, that's the key idea today. It's the P, it's the E, that's the coercivity, that's the intrinsic. Okay, so finally we can go to the PFM. So the PFM is the AFM-based technology to study the piezo response. So the idea is very easy. So if we have a material is piezo response. And then we apply a voltage, we apply an electric field on it. And then the shape will change due to the converse piezo effect. So we net a probe to park on it. And then we apply an electric field. We apply an electric field. And then the shape will change. Since the probe is parked on it, so you can imagine the probe will change deformation. So there will be a deflection. And this deflection, in principle, should equals to deformation. Deformation of my sample. And the deformation in the definition, it should equals to the strain times the thickness of my sample. I define it as height. Right? The strain should equals to what? To the piezo effect coefficients times my electric field. Okay, how I apply this electric field? Easily, I ground my sample. I apply a tip bias. I can apply a voltage, or I can apply an electric field on this sample in the Z direction, right? Or I can do it opposite way. I ground the tip. I apply sample bias. Right? Either way it will work. We just apply a bias on the tip or on the sample. And then with this bias, what's the electric field? The electric field is just the voltage divided by the distance. So this one is just the voltage I applied. So it's the D, sorry, I used the red pen. So it should equals to D times the voltage I applied. It can be tip bias. It can be sample bias. Okay, so I apply a voltage on the sample. I check my deflection. I can get the coefficient, the piezo effect coefficient. And since we apply the voltage, we apply the electric field in the Z direction. And my probe is bent. I'm sorry, the crystal elongated also in Z direction. So this one should be D33. Right? So that's the whole idea of the PFM. We let the probe park on the surface. We apply a voltage. We check the deflection of the tip. That's the PFM. Okay? So any problem with this setup? This deflection will be what? Will be picometer level or nanometer level. Right? It's so small. For detect such small values, it can be easily affected by the environment. I make some sound, the probe will change. I just make some vibration. This deflection will change. So this one is easily affected by the environment. How we avoid it? We do modulation and demodulation again. The same thing we did yesterday. We used telephone theory to do it. So we gave the voltage to be modulated. So this omega can be anything. So it only needs to be kilohertz. That's enough. So we gave it a modulation, and then our deflection will also be modulated. And then what we will do, we will get the amplitude of the deflection. It will equals to D33 times keep values or sample values. Right? That's the way we do it on the piezo response. So we apply a AC voltage on the sample, and we check the amplitude of our deflection. That's the idea. Okay? So with this idea, we can already to study the piezo response, and we can use this to study the piezo response, and the frequency can be anything. Okay, so if we want to study the ferroelectricity materials, so it will have some change. So if we have a materials, it is ferroelectric, and the ferroelectrics, as we said, in principle, it should have two solutions, or it should have domains. So for example, we have this domain facing up. We have this domain, I'm sorry, I use a blue pen, facing down. And then I apply an electric field in this direction. I apply an electric field in this directions. So with this electric field, I just assume this electric field is smaller than coercivity. So I would not change the direction of my domains. It just changes the polarizations. So it will follow what? The polarizations equals to the polarization coefficient times the external E. Okay, so the only idea is how it changes. For this one, if I increase the electric field, so for this one, the polarization will increase. But for this facing down, the polarization, I apply another directions, the opposite directions. So I would shrink the polarization. So for a ferroelectric structures, its polarization, once we change the electric field, its difference or its change should be related to our electric field. So I would say the delta P equals to alpha times the E, and this delta P is increased. And for this area, it's also delta P equals to alpha E, but this delta P is negative. So I can write it down in this way. The positive delta P, the delta P equals to the alpha E, but this one, I write it down, delta P equals to the negative alpha E. Okay, then I make my electric field to be modulated, to be sine omega t. Then I add it here. The delta P equals to alpha E sine omega t. So this one will be delta P equals to negative alpha E sine omega t. Then I hate this negative. So I put this negative inside the senoid. to be alpha E times sine omega t plus pi. And then I get this out. The amplitude is alpha E. The amplitude is alpha E. And this one, the phase is 0. This one, phase is pi. So we get the series back into the PFMs. So we can using the amplitude to get the D33. And then we can use the phase to get the D33 direction. Or we get the polarization's direction. And so the phase from this discussion, it can only be 0 or pi. So it has only 2 directions. And the theory will tell us, and usually the textbook will say the phase inside the PFM, they should have a 180-degree difference. That's because the phase here is just tells us it changes directions. Okay, so the phase is only 0 and pi. Okay, so we have in the textbooks we will have a long description about in the ferroelectricity, in the ferroelectric materials, how the D33 is related to the intrinsic polarization. It has a defined relationships, but this proof it's maybe 2 or 3 slides. So I jumped this. I will send it out in our e-copies. We can show you. If you need this for reference, you can just check it. And it's the same. We still use it following the tensor structures. So, but it's a long improvement. So I jump. I just assume the D33 is related to the polarization, and it's kind of something about this, but the theoretical improvement is quite long, so I just put it in the e-copy. Okay, so we accept this, so we can accept. We study the D33. We can understand the polarization. We know the value of the D33, we know the value of the polarization. We know the phase, we know the direction of the polarization. That's the total idea of the PFM. Okay, and then in the afternoon, we will finish the PFMs. We will talk something about the details of the PFMs, how to choose probes, how to adjust the parameters, blah, blah, blah stuffs. And then we spend some hands-on sessions also on the PFMs. We take a sample, it's the PZT, and we use that to demonstrate how the PFM works. And but in your future works, the first thing I suggest you do is structure study to convince yourself it is ferroelectric, and then we do the PFM or the other analysis. Okay, so thank you for your time. So we will continue this topic in the afternoon at 2 p.m. Okay, yeah, thank you so much. Thank you.